So welcome everyone to the AATRN seminar. The speaker today is Simon Willerton, and he will tell us about instantaneous dimension of finite metric spaces via magnitude and spread.
Right, thank you very much for the introduction and the invitation. Yes, so as was said, I hope this works in terms of pinning me to Zoom and things. A little bit of an experiment, so yeah, let me know if it's not working. Okay, so this is the Applied Algebraic Topology Research Network, but I think maybe the talk today is kind of applied category theory. I mean, we're not going to see any category theory, but it will get a slight mention. So the ideas here come from category theory. Kind of originally, but as I say, that will be not very visible today. Okay, so the talk here is about instantaneous dimension of finite metric spaces. So what do I mean by a notion of dimension of a metric space, or even instantaneous dimension? So let's start with an example, and hopefully this is going to work. Let me just slow this down a little. And so the question is, here's a finite metric space, not a very interesting looking one, but you can see a finite metric space there. And the question is, what is its dimension? So you might have an idea what you might think of the dimension of that. So what I'm going to do is I'm going to zoom in on the space and see if you change your mind. So let's see what happens. So what's the dimension? Okay, have you changed your mind yet? Let me slow that down a little more. What's the dimension of that? What's the dimension of that? Okay. What's the dimension of that? What's the dimension of that? Etc. etc. And what's the dimension now? Now. And I mean, there's no right answer to the question, but I mean, what do you think of as the dimension might well change depending on the scale. As we zoomed into that, we saw that although it looked originally like just some sort of zero-dimensional dot, as we zoomed in on it, we saw that it was like a long strip, and then a strip which seemed to have width. And then as we zoomed in, we saw that it was just made of a load of points. So it was probably a very large scale, looked like a zero-dimensional thing. So what I'm trying to do in this talk is quantify that thought process in some way. So how do we associate notions of dimension that agrees with the sort of intuition you had on that little movie there? Okay, so we're going to start off with a notion of size. So we're going to head to dimension, but to define that dimension, we need some idea of size to do that. So the first notion of size I'm going to look at is this notion called magnitude, which was due to Tom Leinster. And Tom was thinking about metric spaces in terms of enriched category theory and how classical Euler characteristic could be generalized to category theory, and then from that to metric spaces. So there's a whole sort of category theory story behind that, but I'm going to ignore that and just dive in really with the definition. So we've got some finite metric space, X with the notion of distance D, that's going to have capital N points. So for this metric space, I'm going to define a weight of every point in the space. So the weight is going to be a real number, such that the following equation holds. So for each point in the space J, we're going to have the sum of the exponential times the distance to the point I times the weighting of I is equal to 1. Now let me try and make that a little bit more concrete. So suppose that we are the metric space. I'm just trying to see how many people there are. It's probably about 20-something people here. So we're a 20-something point metric space spread out over the Earth, and let's use the geodesic distance on the surface of the Earth. And so what we want to do is associate a weight to each of us And so I'm going to think of this as like being somewhere, the weight is like some kind of heat. So each of us has to generate a certain amount of heat, which might be negative, which means we're sort of generating cold instead. And the idea is that this heat decays exponentially with distance. And what we want to do is we want to arrange so that the heat that each of us generates is such that all of us experience a total heat of 1. So we're all at the sort of same coziness in terms of heat. So I generate enough heat so that the people near me are warm enough, etc. So that's sort of one way of thinking about this weight equation and what these weights are. And then we define the magnitude. So if such a weighting exists, then we define the magnitude just to be the sum of those weights. So the total heat, if you like, that we're generating in order to keep us kind of cozy at unit temperature. So let's have a look at an example. So we've got a 3-point space here. So the idea is that we've got, and I've got to remember to reverse my hands here. So we've got a point, which is about unit distance from these 2 other points, which are really, really close together. And if we work out what the weighting here is, so the weighting is a much bigger on the point that's further away from the other 2. So the idea is that this point here over on the left has to generate a lot more heat because it's further away from the other ones, whereas the other ones are quite close together, so they can kind of share their heat a bit more. And if you add that all up, then you get a magnitude of around 1.47. Okay, so yeah. So do shout out, if there's any questions at any point. Right, so that's the magnitude of this single space, but it gets kind of more interesting. Maybe you got this idea from the video at the beginning. If we look at what happens as we change the scale of the space, so we scale the space up. So if you like, we kind of remove the scale independence by considering all scales together at once. So what we can do is think of the magnitude function of a space where it's the magnitude of the space scaled up by a certain amount. So t of x is just x scaled up by a factor of t. So in this case, we change the distances so that point is t away from those 2, and they're 1,000th of t from each other. And what you can do is you can then calculate the magnitude for every value of t. And I always plot t logarithmically along the bottom, because that's sort of, by doing that, I'm sort of not preferring any scale, as it were. You know, if I plotted that non-logarithmically, I'd be preferring a certain scale. And the idea is I'm trying not to prefer any scale. So it looks interesting when I plot it logarithmically on the bottom. So this is saying that at sort of the sort of regimes, if you like, when t is very small, where all those 3 points are really close together, and it kind of looks like there's 1 point. Now at sort of medium scales, if we take t to be around 10, so we've got a distance 10 here and distance 100th between those points. At that sort of scale, it looks like it kind of looks like there's sort of 2 points. You can't differentiate between the 2 points over here, but you can notice that there's a gap between those 2 and the other point. So in that regime, it looks like there's sort of 2 points. And as you scale up even more, then you see the separation on those 2 points, and it looks like there's 3 points. So the magnitude is kind of telling you, in this example, you know, the kind of the effective number of points at those scales. So this is telling you some sort of some idea of the size of the metric space in some sort of effective number of points. Roughly speaking. Now, so as I said, as t gets bigger and bigger and bigger, these points are all getting more and more widely separated, and so they're all going to have to, they're all going to have to generate 1 unit of heat each. So the weighting on all of them is going to be roughly 1, because of the exponential decay, they can't really see the effect of the weighting from any of the other points. So that's a sort of general fact. As any finite metric space is scaled bigger and bigger, then the magnitude is going to tend to the number of points. Okay, so now that's sort of a nice example, but there are some nasty examples. So here's a sort of a less nice metric space. So we take complete bipartite graph on 3 and 2 vertices, and just make sure the distance t between any 2 vertices that are connected. And if we plot the magnitude this time, then we get something you might not have expected, which is that it's sort of the magnitude, small scales, it looks, the magnitude looks close to 1, and it grows a little, but then suddenly it just drops off. So there's a scale which I think is something like, I should have checked this, it's something like log 2 or something, where or log a half or something, it's got to be less than 1, hasn't it? So maybe it's something like log a half, where there is no magnitude defined. Yeah, so there is no, the weighting can't be defined at that scale. So it's kind of a bit of a weird thing, but asymptotically, I mean, for large t, things behave nicely again. So we'll always get this sort of nice behavior asymptotically, but for some spaces there can be some weird stuff happening at some intermediate scale. So generally, metric spaces are better behaved than this. In fact, there's a class of metric spaces called positive definite metric spaces, where you take the matrix of exponentiated I'm missing a minus. Sorry, this was the last thing I did before coming on Zoom, and I forgot to put a minus sign in there. So it should be e to the minus distance. So if that's positive definite, then the magnitude is well defined. So this metric space up here, this is not positive definite, but a good class of example is subsets of Euclidean space. So they're all positive definite. So in those cases, the magnitude is always defined. Okay, so that's magnitude. Now, as I say, it can be badly behaved at sometimes, but it's sort of got a very rich mathematical life. I mean, as I say, its sort of origins are in enriched category theory, and then we notice that it could be categorified. So there's a homology theory of which the magnitude is the Euler characteristic. So there is some sort of higher algebra going on there. This side is all for finite metric spaces. And it's closely related to notions of diversity for ecologists. So these biodiversity measures.
Simon, excuse me. So we do have a question from the audience. This example is split prime in the sense of dress. Do split decomposable spaces always possess a magnitude?
Short answer is I don't know. Yes, I've not come across split prime before, so I don't know. Good question, I'm sure, but I don't know the answer. Yeah.
Thanks.
Right. So yes. So it was realized that magnitude is closely related to sort of notions of biodiversity, or biodiversity measures, I should say. And Tom Leinster's written a sort of book on entropy and diversity, which is a good read. But I'll come back to that in a very short moment. But as I'll say later, I mean, I'm really talking about finite metric spaces here, but for positive definite spaces, you can extend the notion of magnitude to infinite metric spaces. Essentially, if you've got an infinite metric space, you approximate it by finite metric spaces, and the limit as that approximation in terms of finite spaces gets closer and closer to your infinite space, then the limit of the magnitudes is the magnitude of your infinite space. It's one way to define it. There's other sort of more canonical or less dependency on approximation. So there, this does extend to nice infinite spaces as well, and in that case, magnitudes related to lots of other things like potential theory and special functions. For subsets of Rn, it knows about things like volume, some sort of classical notions of size. And one thing, again, I'll come back to later, it knows something about the Minkowski dimension, but I'll come back to that. So magnitude, although, yeah, it has it for these kind of odd spaces, it can have these singularities. It is a sort of very interesting thing. So let's go to a slightly more boring thing perhaps, but a bit more well-defined. So from the connections with biodiversity, I sort of extracted another notion of size, which I called spread. Well, and this comes, well, the biodiversity measures, the sort of standard ones, they come in a one parameter family. And so I get a similar one parameter family of measures of size. So this parameter is a non-negative and possibly infinite real number, Q. So I call these the Q spreads. So these are, as it says here, closely related to magnitude, but simpler and better behaved. So for instance, magnitude doesn't have an explicit formula. It's defined, write down n simultaneous equations in n unknowns, where n is the number of points, solve it and add the solutions together. Whereas this has a sort of explicit formula. So that's sort of a nice simpler thing about it. Often with these kind of one parameter families, things like entropy and biodiversity, there's some specific values of Q which will give you some kind of simpler formulas with nice properties. So in particular, if we take Q equals 0 or Q equals 2, we get the 0 spread, which has this sort of simple formula here in terms of the exponential of minus distance, and the 2 spread, which has this particularly simple formula as well. So as we'll see, these turn out to be similarly interesting notions of size, but are sort of possibly less rich, but still interesting. I'm saying these are related to magnitude. In particular, if X is a homogeneous metric space, so it's got a sort of transitive action of its distance preserving maps, then the Q spread, whatever value of Q, is equal to the magnitude. So these do recover the magnitude in the case that X is homogeneous. But yeah, so we got these sort of two nice other interesting notions of size. How am I doing time? Okay. So let's have a look at this for this was our 3-point space from earlier. So the black line that's slightly hidden here, that is the original magnitude, and you can see that E0, the 0 spread, is closely tracking that, the green one there, and then the red one is the 2 spread, is sort of similar shape, but not exactly the same. Now this, I said, this is the spreads are sort of more nicely behaved than the magnitude, because you've got properties which you would hope the magnitude would have, but doesn't quite. So in particular, the spread is always between 1 and the number of points. You've got a metric space with n points. The spread is always, somewhere between 1 and n. Let's jump to number 3. It's 1 as you shrink that space down. The Q spread is going to go to 1. So and as you expand the space out, as you get closer, as you send t to infinity, then the Q spread is going to tend towards the number of points, and it is increasing as you increase t. Okay. So if we have a look at our bipartite graph example, a bad space that I mentioned earlier, then what we have is that I've just plotted the 0 spread here. That's sort of a nice version of this horrible thing with the singularity. So it sort of so it has this sort of nicer properties. But as I say, nicer properties, but possibly that means it's a bit less interesting. I don't know. The spreads are far less well studied than the magnitude, I think it's fair to say. Right, so we've got these notions of size, and now we can sort of move to the notion of dimension, which is kind of what I'm really aiming to talk about in this talk. So if we have a metric space, the question is, what should happen to the size when we scale distances? What do we? So I'm plotting these graphs of size, be that magnitude or spread, against distance. But and this kind of has some kind of interesting behavior. It doesn't behave in an obvious fashion if you scale the size. But kind of what happens if we take some nice spaces. So for instance, suppose we triple the distance. If we just take the interval, an interval, and you triple the distance, then what's happened is you end up with a space that's 3 times as big. I mean, there's a subtlety there, which I'm going to gloss. Well, I will explain the subtlety, but I'm not going to say much more about it. If you take a closed interval and you triple the distances, it's not exactly 3 times as big, because what's happening to the endpoints, sort of, if you triple it, you should count those endpoints 3 times, and so there's a little. If you put 3 copies of the interval on top of itself, then there'd be a little bit of an overlap. So it's not exactly 3 times as big, and you can. There's ways of talking about that, but it's roughly 3 times as big. If we'd done the half open interval, then that would have been exactly 3 times as big. But as far as this conversation is concerned, 3 times as big is good enough. Okay, if we take a square and we triple the size, triple the distances, I should say. If we triple the distances, then we end up with obviously something which is 9 times as big, or roughly 9 times as big. Yeah, if we ignore the subtlety about the boundary. Now, if we take a Cantor set and we triple the distances, then just make it 3 times as big. Sorry, we make the distances 3 times as large. Then we end up with 2 copies of the space, and exactly 2 copies of the space in this. So that's 2 times as big. And what's that got to do with dimensions? Well, I'm sort of saying something which you probably know, but just really stressing this point. So we think of the line as being 1-dimensional, and 3 is 3 to the 1. Obviously, that's 3 times 3 to the power 2, where 2 is the dimension of the square, and the Minkowski or the Hausdorff dimension of the Cantor set is log 2 to base 3, and so this is 3 to the Hausdorff or Minkowski dimension. I'm saying, sorry, I should say Minkowski dimension is probably not so well known. It's just a fractal dimension, which is the same as the Hausdorff dimension in many cases, I think, is all I want to say about it. But it's a notion of fractal dimension that agrees with the usual one, which I guess is the Hausdorff dimension. Anyway, so here what we're seeing is that when we scale the distances by a factor of t, let's say, then the size is t to the dimension of the space. So think of the dimension of how the size changes when the distances are changed. So, and given some notion of size, we can see if this gives us a good idea of dimension. So, as I say, we've got magnitude, and the various spreads are notions of size. So can we use these ideas to get a notion of dimension? Okay, so this is where we get to the instantaneous dimension. So suppose we have a notion of size, which might be one of the ones I've just mentioned, or might be something more classical like volume or length or something. Then if the size varies on changing the distances by a factor of t by a dth power of t, then what we want is that the s dimension of the space at that scale to be d. So the idea is that d is encoding the growth rate of the size. Okay, so formally we can do that with the following thing. This is just the growth rate. It's just the sort of logarithmic derivative of s of tx with respect to t, and this is what we're going to define the s dimension to be. Okay. So this is, as I said, this is just the growth rate, and so it will satisfy this property. If the size is just a dth power of t, then this will just give you d as the dimension. So just as with magnitude, we sort of had the magnitude function, which gives us a sort of a profile. We can think of the dimension profile as we fix x and vary t, we're going to get a plot of the dimension, which is going to be the dimension profile. So we'll see some examples of that in a second. We're going to see that for the sort of the following three notions. So we can take these notions of size we had before, so the magnitude, the zero spread and the two spread, and just use this growth rate or idea to define the dimensions. And you can kind of compute these. So we're going to see, as I say, we're going to see some examples. So maybe I should just say something about computing them. So you can code these up quite easily to get some approximations. So I do it in Python, nothing very clever. Well, apart from maybe one thing which I'll mention in a second. So on my desktop with about 16 gig of RAM, I can do it for 10,000 points in a couple of minutes. Now, I don't know how big the kind of spaces people look at, but 10,000 points can seem like a lot to me, unless I'm living in like well, even 6 dimensions. I guess 10,000 points is not a lot in 6 dimensions, because it's going to be, if you take a cube with 10,000 points in it, it's going to be less than a 10 by 10 by 10 by 10 by 10 cube or hypercube. So I feel that when I'm starting to look at higher dimensional things, that's not many points. And so one could probably hope to do things better than I've done them. But that's kind of where I'm at in the sort of naive programming way. Now, magnitude, as I said, magnitude, in contrast to the spreads, doesn't have a nice sort of simple formula that you can write down. You're trying to solve these equations, simultaneous equations, and then add up the thing. So solving that exactly, I mean, that takes order of like a day rather than a minute to, order of days to calculate these rather than minutes if you do that exactly. But there's things like approximate methods for doing this, like Krylov methods, which are naturally sort of written in NumPy and the likes. And then, so you can compute a load of values, you can work out its magnitude profile, and then you can sort of do the approximate growth rate from that. You can just literally work out the sort of gradient of a log-log plot for those points. And as I say, yeah, then the computation can be done in kind of minutes. So then just getting to more theoretical things. I mentioned this earlier, that the magnitude can be canonically extended to infinite metric spaces as long as they're sort of positive definite, which includes subsets of Euclidean space, so balls and squares and things, subsets of Euclidean space. And if you take the asymptotic growth rate of magnitude, so I'm just taking the growth rate at a given t, if you look at what happens as t goes to infinity, then the asymptotic growth rate of magnitude is exactly the Minkowski dimension, which, as I said, is the Hausdorff dimension in the sort of in most of the examples you're probably likely to think of. So magnitude itself kind of knows the fractal dimension, at least asymptotically. So Mark Mecker kind of proved this after I'd done various experiments with finite metric spaces, showing there was some kind of connection there. I mean, this doesn't tell you anything for finite metric spaces, because the Minkowski dimension of a finite metric space is just 0. And we know that as we scale t to infinity, the magnitude curve just flattens out because it tends to the number of points. And so the growth rate asymptotically is 0 because it just becomes a constant. So for finite metric spaces, that isn't telling us so much, but as you'll see from some examples, I mean, that's still living in, a ghost of it is living in finite metric spaces. Okay, so I'm at the half-hour point, so I guess I've got about 10 minutes left, and I should give you some examples. I'll just pause for a second if there's any questions at this point. I always feel, you know, when I'm talking to a camera, I always gabble a lot more than if in front of actual people. So I apologize if I've been gabbling. Anyway, right, let's move on to my clickbait quiz. Okay, so so this is supposed to be audience interaction, but I don't know how well this is going to work over Zoom. So feel free to shout out. So I'm going to give you 10 examples, and I'm going to plot the dimension profile. So I've sort of mixed up the magnitude E0 and E2 because they all actually look quite similar for these metric spaces. And just for computational convenience, I used one or the other, but they all look pretty similar. So the quiz then is I'm going to show you a dimension profile, and you're going to have to guess what the point cloud was, what the finite metric space was that I started with. Okay, so the first one is this. So kind of at small scales, it looks like dimension 0. So it looks like it just points. And then at a certain regime, it looks like it's a bit bigger than 0 dimensional. And then it's sort of 0 dimensional again, and then a bit bigger than 0 dimensional again, and then it stays at 0 dimensions. Anyone want to have a guess? Okay, so it's not an obvious one, but it's one that I've mentioned. Okay, so this was our little 3-point space. So the idea was that so the one where you had the 2 points. Sorry, 2 points clear. Yeah.
Simon, excuse me. There is a guess from the audience, some homogeneous space.
Sorry, I moved the chat off the edge of my screen. So right, yes. So some homogeneous space. So as Marcus has commented, yes, that's not what it was. I mean, I don't think there's a homogeneous space that this will work for. But anyway, let me tell you. So at small scales, yeah, it just looks like a point, so 0 dimensional. As you scale it up, you get that separation between the 1 point and the 2 points, but the 2 point but then as it grows, so it looks like it's got a bit of a width to it, and then as you move them apart, you see the it looks like there's 2 distinct points. You've got the single point and the clump of 2, and then so it looks 0 dimensional again, and then as you scale it up, you can see that you start to get a little bit of sort of height to those 2 points, so it looks like it's more than 0 dimensional, but then they move apart and it looks 0 dimensional again, as we've got 3 points. Okay. So that's sort of the thinking behind that profile. Okay, so profile 2 then is this one. So it starts off that it looks like there's 0 dimensional at small scales, and then at sort of intermediate scales, well, it's close to being dimension 1, but then as we scale it up bigger and bigger and bigger, it sort of looks like it's 0 dimensional again. Anyone want to have a guess at that one?
Sample of points on a line.
I heard points on a line. Is that what you said?
Yeah.
Yeah, exactly. It's 1,000 points in the interval 0, 1. Yeah. So if you really close together, and then as you sort of scale up, it looks like it's an interval, certainly when you're sort of width, you scale it up by a factor of 100, you've got sort of a length 100 interval with about 10 points per unit. But then as you scale it up bigger and bigger, then it sort of loses its lineness and looks like a load of points again. So that's what that's doing. Great. Okay, how about this one, where it just looks like it's dimension 1 for longer. More points on 0, 1 is what Marcus says. And that's exactly what it is. Of course it is. So this is 100,000 points in the interval 0, 1. Is that. Okay, so moving on then, profile 4. This looks like it's 0 dimensional, and then it looks at sort of intermediate scales like it's sort of nearly 2 dimensional.
Points sampled from the disk or the square.
Yes, exactly. 270 by 270 grid of points in this case. How about this one? So at some scales it's 0 dimensional, some scales it looks kind of 1 dimensional, and then some scales it's looking, as we make it bigger and bigger, it's looking 2 dimensional.
Maybe point sampled in a rectangle?
Exactly, yeah, great. So this is a 12 by 600 grid of points. Yeah, so yeah, you just have to make it computable and make it wide enough and long enough for this effect to kind of show up. Yeah, exactly. So this is basically the example that we saw in the animation right at the beginning. How about this one? So, I mean, a good answer to this. So what is this? So a good answer to this is an elephant being eaten by a boa constrictor. If any of you have read The Little Prince, that should be familiar. But anyway, mathematically, what do you think it is? Okay, so this one is 2,000 points in a circle. So the idea is that it sort of looks like a point because it's really squished up. But as you make it bigger and bigger, it's actually got height and width. It hasn't just got, like as we had in a line before, has height and width. So it sort of looks like a blob rather than a line, which is why it goes to be a bit more than one-dimensional. But then as it gets bigger and bigger, we can just see that it's a sort of a line of points. It's just one-dimensional set of points and then drops off again. Okay, and this one, well, from what we said before, this is just more points on a circle because it looks one-dimensional for longer, because as you scale it up, it looks, yeah, one gets that sort of one-dimensional effect at larger scales. How about this one?
Maybe point sampled in an annulus?
Exactly. That's exactly. I can't see who said that, but yes, exactly. So it's what's that? 10,000 points in a noisy circle in the plane. So yeah. So I've taken a circle and added a little bit of noise, so you can think of that as being in an annulus instead. Yeah. So you get that. So it looks like it's a circle until a certain scale in which you realise that the circle is a little bit fatter than you thought it was. Exactly. Great, you're doing splendid. And how about this one? So it looks like it's zero-dimensional, and then for a long time it looks like it's 0.63 dimension.
Point sampled from the Cantor set?
Exactly. So 0.63 is whatever the Hausdorff dimension of the Cantor set is. It, what is it? Log 2? Log 2/3. I think it's log 2/3, isn't it? No, something like that. Sorry. Yeah. My mind's just gone blank. Now, the interesting thing here is what happens if we zoom in. So there we go. Yeah, log to base 3 of 2 is what it is. I knew there was a 2 and a 3 in there. So if we zoom in, there's sort of this interesting phenomenon happen, and this happens with the magnitude for the dimension for magnitude, the 0 spread and the 2 spread. I think this is the 2 spread that has this little strange lump at the end. But if we zoom in to this profile, we see it has this kind of interesting behavior around the Hausdorff or Minkowski dimension. So in fact, this is kind of logarithmically periodic of period 3. So every time you scale up by a factor of 3, that's where this kind of wobble comes back to itself. So yeah, if you have the Cantor set and scale it up by a factor of 3, as we saw, it's sort of self-similar at scaling up of factors of 3. So that's kind of being reflected in this dimension. I don't really understand this phenomenon at all, but it's kind of interesting that it happens. Great. So Mark Mecker's had this result that it, for the actual Cantor set, the magnitude growth rate asymptotically is log to base 3 of 2, but we're actually seeing this in a finite approximation to the Cantor set. We're seeing that that Hausdorff dimension as well. Okay, and then finally, for the last one, we've got this one, which is log to base 3 of 4, it looks like. And so you can remember what kind of shape has a dimension, Hausdorff dimension that's that.
Snowflake?
It's not the snowflake. I think I could have put the snowflake. It's the Sierpinski gasket. Yeah. So the snowflake is something similar. I would have guessed either the snowflake or the gasket. Yeah. So it's a Sierpinski triangle. So again, you've got that sort of phenomenon. So as you can sort of see from those examples, you know, we are getting interesting kind of phenomena out there. But these are all, as I said earlier, in terms of computation, these are all kind of low dimensional examples. I think to see higher dimensional phenomena better, I would need quite a few more points in my sort of point clouds, if you like. But the sort of interesting information going on there is really the point. So the challenge, you know, you can have a look at dimension profiles for some interesting data sets. I know that I should mention, I've not got it written down here, that Kevin Dunn has a paper on the archive where he's done this for some psychology data sets and a snake eyes data set. So he's made a start with some of these things. Anyway, so that's really where I wanted to end, just showing you some examples of these dimensions in action.
Thank you so much. Perhaps before we get to questions, I would invite everyone to unmute themselves so that we can clap for Simon. Okay, so time for questions now.
Hi, I have a question.
Please go ahead.
Thanks for the great talk. I was particularly interested in this image that you said with the heat, that we can think of magnitude of a point. No, what was it? The weight of a point as how much heat we radiate. Can we think of this as some kind of outlier score of a point?
I don't know. It's not something I'm familiar with, so I don't know. Okay,
or maybe if it's if points with a high weight, are they far away from the barycenter or something like this?
Yeah. So, well, I mean, so you can get some kind of strange things happening. So, just trying to think if I can easily find an example for you. But I've got this computation. So if you take just a square in 2 dimensions, I take an n by n, capital N by n. Oh no, the square root of that. So just take a k by k square. So you've got k squared points. Let's say and you make it fit it into the 1 by 1 square in the Euclidean space. So that grid. Then what can happen is you get some of well, what you're supposed to think of here is like penguins packed on the Antarctica, all gathering together for heat, and the ones on the outside are going to have to generate more heat than the ones on the inside. So the phenomenon you see is that on the outside, on the boundary, you get a lot higher weight. In the middle, they're all pretty similar, but on the outside, they're really high. And the bizarre phenomenon you see is sometimes, depending on the scale and the number of points, sometimes the next row in actually has to have negative weights because the ones on the outside just have to generate so much heat that the ones next to them have to kind of generate coal in order to kind of compensate for the stuff coming on either side of them. So, so in that case, yeah, then 4 corner points get particularly high weightings on them as well in that example. So I don't know if that's a helpful example for you or not.
So yeah, it's very helpful. Thanks.
So we have a question from Emmanuel Delucci. Please go ahead.
Yes. Hi. Thank you for a great talk. I have a question about
I mean, you associate now to every, let's say, point configuration or whatever metric space, you associate one of these profiles, right? So I want to know if there is a nice or canonical way to measure distance between profiles so that one can classify these metric spaces by looking at profiles. Is there a nice space of profiles that makes sense?
Again, you know, there's so much, so many good questions people can ask that I just haven't really thought about. Yeah, so I don't know. Yeah, yeah, I would hope so, but yeah.
Yeah, if anybody knows anything about this, I would be interested. Anyway, just a shout out there. Thanks again.
Thank you. So then Abby Hickok is next.
Hey, thanks for the nice talk. I was wondering if you could say anything about maybe like the convergence of these dimension profiles as, say, like the number of points is increasing. Like, let's say I'm sampling for a manifold and I sample more and more points.
Right. So, I mean, what seems to happen, let's go back to...
Yeah, you showed like
even,
one example.
Yeah, even that sort of example. It seems that empirically, and I don't have much more than empirical results for any of this dimension stuff. It seems that it sort of stabilizes and you're just getting better information at higher scales. So the stuff down at the bottom end looks pretty much the same, and then so you're just getting more information at higher scales. Yeah.
Okay, thanks.
Yeah, I mean, certainly, yeah. I mean, lots of, like the Cantor set, I've sort of experimented, you know, done various things with the Cantor set, and you just get more wiggles coming on here. For instance, yeah, that doesn't change at all if you add more points.
Okay, so then we have a question from Henry.
I had a question. You gave some really nice examples differentiating the spread from the magnitude. Could you say a little bit more about the formula for the spread, how you came up with this equation?
So the general formula, for instance, yeah. So as I said, this comes out of the biodiversity stuff. So so the idea is, so what's magnitude got to do with biodiversity? So the idea is that in biodiversity, you're looking at how diverse ecosystem is, and your ecosystem is made well in typical models. You think of your ecosystem as being made up of species, and exactly what information about those species you take into account will affect how you sort of define your diversity measure. So classically, what people did was they just looked at the relative abundances. So you walk around your garden and you see how many of this flower you've got, how many of that flower, how many of this tree you've got. So you look at the relative abundances. So you'll have what is essentially a probability measure on your space. You'll have a set of points and a probability measure on it, and you use that to determine the diversity. So if you have 3 species and all relatively with probability a third each of them, they're all equally abundant, then that sort of has diversity 3. Whereas if one of the species is dominant, has sort of relative abundance 0.99 and the other 2 share the rest, then that's got diversity approximately 1. Now, you can take more information into account. You could say, well, you're ignoring how related the species are. So it might be that two of these species, you might be a farmer and you've got a field which has barley and wheat in it, and another field which has dandelions in it. So 2 similar cereal crops and then a field of flowers. And you might say, well, that's closer to sort of diversity 2 than it is the diversity 3, because you're taking into if you were to take into account the difference. So then you model your ecosystem as a metric space, or a space with not necessarily a metric space, but something of that ilk, where you've got distances between the species, measuring the difference as species, together with a probability measure on which is, say, how relatively abundant things are. And what Tom Leinster did was he combined magnitude, which is saying about metric spaces, with the classical measures of diversity, which just involve the sort of the relative abundances, to a measure of ecosystems where you take into account the difference between species as well as the relative abundance of species. And that was his, well, him and Christina Cobbold, I should say. And so my measures then, so what I do is then I think of my metric spaces. So he ends up with a family of biodiversity measures. And so what I did was I said, right, okay, so I'm thinking of my metric spaces as having a probability measure on them. I'm just going to use his measures where I take the uniform probability measure on. So I'm just saying all my species are equally abundant and use that as a measure of the size of metric space. So that was a kind of a long story. I mean, then the question is, where does Tom's formula come from? But so that's where I got the formula from. So it's sort of this biodiversity measure where I just assume that all the species have the same abundance in them.
Thank you. Very nice.
More questions? Okay, so thank you very much, Simon. So I will stop the recording now, but we can still take questions offline.